Welcome to ATMOS 5000 Day 7. Our objectives are from Chapter 3, Section 3.4. We're going to define the environmental lapse rate and adiabatic processes. We will look at how dry adiabatic lifting of an air parcel will affect its temperature with height. We'll define a potential temperature and virtual potential temperature. And we will use Poisson's equations to determine how temperature, pressure, and the specific volume of an air parcel change with as it moves up or down in the atmosphere. And lastly, we will introduce thermodynamic diagrams. The environmental lapse rate in its most simple form is just seeing how the temperature changes with height. And we actually define the lapse rate gamma as minus delta T over delta Z. We typically measure it with a Raywinson balloon system. So we launch a balloon and it has an instrument package on it that measures temperature, pressure, and dew point temperature with height. And then we can also get the wind speed and direction at different heights as well. And these balloon soundings are really useful in determining the stability of the atmosphere and whether or not there's likely to be thunderstorm activity in the afternoon. To summarize the previous lecture, if an air parcel is lifted dry adiabatically and there's no exchange of mass or energy with the environment, by definition the dq in the first law of thermodynamics is equal to 0, and the dry adiabatic lapse rate in this situation, gamma d, is equal to 9.8 degrees Celsius per kilometer. And if these conditions are met, namely dry and adiabatic, then the temperature of an air parcel will always decrease at a rate of 9.8 degrees Celsius per kilometer if it's lifted upward. In practical terms, if we start off with an air parcel at 20 degrees Celsius at the surface and lift it 1 kilometer, its temperature will decrease at the dry adiabatic lapse rate, and it'll be almost 10 degrees Celsius colder when it reaches 1 kilometer. In contrast, if we take that same air parcel at 1 kilometer and then move it back down to the surface, the process is reversible because the parcel will still follow the dry adiabatic lapse rate, in this case warming by almost 10 degrees Celsius per kilometer. Potential temperature, as defined in the lecture, is the temperature to which an air parcel will have if it's moved dry adiabatically to a pressure level of 100 kilopascals. In the video, it was referring to 1,000 hectopascals, but the Stull textbook does everything in kilopascals, so I've basically redone this equation here with P naught being equal to 100 kilopascals. The virtual potential temperature is a slight correction to the potential temperature that includes the water vapor mixing ratio effects on the parcel density. And virtual potential temperature will be used a lot when we start to work on atmospheric stability and buoyancy differences in the atmosphere. During adiabatic ascent, the temperature, the pressure, and the specific volume are all changing. Unfortunately, the first law of thermodynamics equations, which we have looked at previously, only have 2 variables in them. Thus, we have 3 unknowns and 2 equations, which doesn't allow you to solve the problem. However, by combining 2 forms of the first law of thermodynamics, it is possible to reduce the dimensionality of the problem from 3 variables to 2 variables. The resultant equations, which are shown below, are known as Poisson's equations. In the top equation, we have P alpha raised to the gamma power is equal to a constant, where gamma is equal to C sub P over C sub V, which equals 1.4. The second equation is T alpha to the gamma minus 1 equals a constant. And the third equation is temperature times pressure to the minus kappa equals a constant, where kappa equals the gas constant R divided by C sub P. Using Poisson's equations, the first question to ask is this dry adiabatic process? If it is, then you can use the Poisson's equations, and this is how it's typically done. So if we look at the first equation, P1 alpha 1 to the gamma is equal to a constant, which is equal to P2 alpha 2 also raised to the gamma power. So if you have an initial condition of an initial pressure and initial specific volume, and we lift an air parcel to pressure 2, then we can solve this equation for the specific volume at altitude 2. Similarly, you can do that with equation 2 or equation 3. You just need initial conditions and then some kind of change to the system, and the equations will allow you to calculate the last variable that you need. And lastly, we are introducing some thermodynamic diagrams. This is a Stuve diagram. The x-axis is temperature in degrees Celsius, and the vertical blue lines are the temperature. The y-axis is pressure, in this case in hectopascals. Recall that 1,000 hectopascals or millibars is equal to 100 kilopascals. And the solid green lines in this case are your dry adiabats, or lines of potential temperature, and also what we call dry adiabats. Another type of thermodynamic diagram that we use is the Skew-T LogP diagram. It's very similar to the Stuve diagram in that it has the temperature on the x-axis and pressure on the y-axis, but what it has done is it's skewed the temperature so that they're no longer vertical. In this case, the solid red lines that slope up to the right are the temperature, are the isotherms, and in this format, the solid green lines are no longer straight lines, but they curve up to the left, and those are the adiabats, or the lines of constant potential temperature. And you'll see a lot more of these thermodynamic diagrams as we move forward with thunderstorm prediction.